Okay. So at least we are something. I don't know. There must be something. I wonder if we'll see on the news later. There was an iCloud problem because I've been having issues with it all day. All right. So let's talk about the midterm. Yeah, see, they can't even connect to iCloud. So I'm going to just say I'm going to edit a copy so it can at least function here. Yeah. So I think Apple must be somewhat dead in the water. All right, so midterm. It will be on Thursday. There will be 10 questions. My typical thing, 10 questions, 10 points apiece. Oh, one other thing before I forget. Also, Hackathon. Was it November 17th? November 17th, 8 a.m. to 8 p.m. What's up?
Just an announcement after you finish this.
Okay. So, this is required for all of my classes. If you aren't able to make it, there's a really, really, really nasty assignment, penalty assignment. So, in any case, mark this in your calendars, ask for work off, whatever you need to do. Should give you plenty of, this is almost a month from now, so hopefully plenty of advance notice, but if you prefer to do the penalty assignment, you can. This year, our topic is going to be machine learning. So I'm going to do a boot camp on the, probably either the Tuesday or Wednesday, possibly the Monday before that, one of those 3 days. I guess in a worst case Friday, but definitely not Thursday. One day before the week before that, I will do a boot camp. I'm evaluating either IBM Watson or Amazon's ML machine learning. So one of those two platforms I'll pick is the one that's going to be the one that'll benefit you most in the industry, and B, can come up with the best examples or something like that. I'll do a boot camp crash course thing on it. If you're not able to make that, I will record it, so it's up online. You can go and view it. And then I'll try to put teams together relatively early, so I need everybody to sign up as early as you can. Just email Professor Josh Locklear, joshua.locklear@cuw.edu, to get your name on the list so I can put together teams. You can start brainstorming ideas in the week or so ahead of the hackathon. But in any case, are there any questions about hackathon? Good? All right, everybody has the date on their calendar? Just make sure I do. Go ahead.
Then slightly less long-term notice, tonight, 8:30, in Pharmacy 008, we have an event called Hackathon Unplugged. It is going to be a zero-tech kind of short little hackathon. Gonna write out an algorithm on paper. Should be a fun time. I encourage you all to come, send your friends, get people interested in computer science.
Here, hackathon, Muath. You got the date? You got it written down?
Yeah, 17 November.
All right. Yeah, actually, from what I've heard, previous penalty assignments have been actually too short. So, too short. They say it was only like 12-page paper. I think I'm going to make it longer this time.
Book?
There must be a minimum of four chapters. must be 4 chapters. Or I can go full-blown Christian worldview and just like to have you transcribe the New Testament. That'd be kind of fun, actually. That would kind of be an evil assignment. You have to do like the whole thing, just transcribe it.
Figure out how to procedurally generate the Bible.
I don't think that
create
works.
A program where a specific seed will plug in and give you the actual text of the Bible.
So, okay, so randomize the text of the Bible. What language? What's the base language?
English, probably.
Okay, well, and then, I mean, now you're not in the original languages, so.
Yeah, but then you can make an argument, though. Do we even know for sure what the original is?
You're right.
I mean, because all the different Greek manuscripts have slight differences.
Right, but we're pretty sure it wasn't English.
Well, yeah.
So, I mean, we can at the very least, we can start with that.
Hebrew, Greek,
Yeah. We're definitely not English.
Translate into jive.
All right. So, 10 questions, 10 points apiece. It's the usual thingamajiggy thing where if you do better on the final exam than you do in the midterm, I'll replace your midterm exam score with the final exam score. So, everybody in here, I think, is familiar with that. All right. So, I'm going to go ahead and I'm going to go through all the slides up to this point. Pointing out what things I think seem important and what things seem less important, so you kind of know where to focus your studying. Okay, and I know at some point things got in a kind of a wonky order because I was starting them in a weird place, so if things seem out of order here, just, I guess, deal with it. I'm probably not going to ask kind of generic computer part questions and stuff like that. This was kind of a background type thing for kind of, we needed to get down to the level of computer architecture that we start caring about, so the CPU and how the memory interacts with that and that kind of stuff. So, we're not going to talk about the components of a computer, probably not on we'll call that a 1% chance if I get like completely desperate for a question. Okay, but if that's the case, I'll just throw another conversion question on there. So it's close to a 0% chance of something like this is possible. Same thing with like the various CPUs. This is more just kind of introducing the idea of CPU architectures. So at the very least, you should be familiar with that concept, that different CPUs have different architectures associated with them. And when I say architecture, what am I really talking about?
The internals of the processor are organized.
Okay, so that's the hardware aspect of the of an architecture. What's kind of the software component of it? Would be the instruction set. Oh, yeah. So the instruction set of a particular CPU. So this is the list of magic tricks that CPU understands. So you look at the Intel CPUs; they're going to be supersets of the previous one. With every now and then they take away an instruction or something like that. What's the problem? So, for instance, I could ask a question on the exam along these lines. What would be the ramifications of, let's say, Intel removing an instruction or drastically changing how an instruction works in the next version of its processor? Why won't they do that? Go ahead.
Because any programs written for the previous instruction set processor won't work on
Yeah,
the new
they'll
one,
break.
vice versa.
Yeah, so when you have, like, you look at the side of a piece of software, even though you don't buy it in a box anymore, but, if you look online and it says, minimum system requirements, Windows 7 or something like that, what they're effectively saying is that, if you're talking about Windows 7, you're talking about here's the system calls, the operating system calls that this guy's written in terms of. And similarly, it's going to be also representative of what Windows 7's minimum system requirements were in terms of what CPU class is the oldest that Windows 7 will run on. Because at some point, Microsoft had to make the decision where, I'm going to write this operating system to run on this CPU and newer. Even if they decide that this CPU itself might have sketchy performance, they're at least picking a starting point instruction set, a bare minimum instruction set. That make sense? All right, so when we talk about CPU architecture, we're talking about, from our perspective, maybe more about the instruction set. From a, electronics perspective, maybe we're kind of talking about how a processor is actually put together and how L1 cache and L2 cache are actually linked up and stuff like that, the wiring. We're less concerned about the specific wiring. We're thinking about it more maybe at a software integration layer, how we talk to the actual hardware. All right, so I won't ask questions about a specific processor, history of processors or something like that, but you should certainly be familiar with the idea of an instruction set, be familiar with that concept we just talked about where when something has a minimum requirement, it's really talking about when you compile a program, what does a compiler do? What's the purpose of a compiler? Go ahead. Okay, almost. High level to low level. Yeah, in the middle. Yeah, machine level gives us our zeros and ones. And we've seen recently where we've taken that low level and converted it to the machine level, right? The zeros and ones. So we've done that last little step. And that does happen when we actually link an executable. But the compiler itself, it does the job of converting from that high level language into that low level language. And once we're in that low-level language has a one-to-one relationship with the CPU, right? So that guy is the output of the compiler, which is going to be a whole bunch of magic tricks, instructions to that CPU, and they all need to be present on that CPU. So if it calls some magic trick that the CPU doesn't know how to do, because you're running on a newer processor that's removed that magic trick, program breaks, assuming you hit that data path. If you never hit that if statement, you never get into that magic trick, maybe you luck out. But generally speaking, that's where the compatibility problems come in. So, we could say that generally speaking, a new processor is going to be a superset of the last many processors. At some point, they might draw a line and say, look, we're going to deviate because the old way of doing it is no longer a viable way of doing it. But we can expect that anybody who's going to legitimately be running our software is running a new enough computer that it's going to have a newer architecture. We've seen the same thing when we first started an Android project or something like that. It asked you what API level you want to start with based on how many, the number of active Android devices that are out there that are running at least that level of the Android OS. Kind of the same type of thing. They're writing their software in terms of, it's been compiled in terms of the system calls that were available in that version of the OS. So they're at the mercy of those system calls still being around. All right, that makes some sense? Okay. So there's your CPU instruction set. That's what we just talked about. Just talked about that. We're probably not going to care too much about clock speed. We did mention it in class as kind of, we can almost think about it as like millions of instructions or even billions of instructions per second. But with different architectures, those aren't necessarily we're not comparing apples to apples. So nothing on clock speed on the exam. This is another thing. This is more kind of current state of hardware. Also won't talk about this. Very large scale integration, VLSI. This is the technology we're using to produce the chips. And, what we're doing now is we're getting the wires. We have, we kind of printable circuit layers now. So the wires get as close together as possible so they don't interfere with each other. So we're at the nanometer. I think 7 nanometer either were just announced or I think they were just announced. I don't think they're out, but whatever. It's tiny. The space between wires is very, very, very tiny. Okay? So that's what this whole nanometer thing is. Won't be on the test. More of this is what the hardware side of things kind of looks like today. Possibly a question that deals with the idea of single core versus multi-core. I maybe would have to be a little desperate for a question because I don't want the focus to kind of be on that, but we should understand that when you have multiple cores in a CPU, you have the instruction set, the architecture duplicated more than once. So each of those cores is capable of the entire instruction set. Well, generally speaking, each of those cores is capable of the entire instruction set. I think when we had this slide up, it was around the same time as Apple had announced the new iPhones. I think we talked about the new processors, and so there's 6 core processors, and 2 of the cores are low power cores, but they actually have a reduced instruction set. So they are more domain specific cores as opposed to general purpose cores like the the faster cores in there. So they would actually have a reduced instruction set where you can only do certain things on them. But generally speaking, if we're talking about multi-core CPUs, we're talking about duplicating the instruction set across the multiple cores, and each core can do one thing at a time. Okay, so from our perspective in here, there really isn't a difference between single core and multi-core because we're thinking about things in terms of instructions being processed by a core and then how it interacts with memory and stuff like that. Whose job would it be to manage multiple cores? Which course would be in charge of the concept of managing multiple cores?
Operating system.
Yeah, operating system class. Okay, so now that's where we start thinking about, we have a quad core processor that the operating system's scheduling for. How we're in this class, we care about how one of those cores works. If you have 10 of them, fine, but this is how one core works. Now we have an operating system that's scheduling for the resources of the computer, and if you have 4 cores, you have 4 cores, and has to figure out how it works. All right, so like I said, I'd have to be pretty desperate to ask a question about multi-core, and it would be a easy kind of throwaway question because from our perspective, it's just the instruction set duplicated more than one time. Nothing to benchmark. The concept of hardware versus software is something you should be familiar with. Same thing with firmware. If I remember correctly, Alexis came up with firmware in class. Am I remembering that right? So that's our hybrid, right? Because once we have hardware, we got everything, in the old days, everything soldered together. That's it. Now things are more printable, so but the point is once you've produced 4,000, 4 million, whatever of these components, you're not changing them. So you got to get that part right. So now what a lot of hardware has is a firmware component where it's a computer on a chip that talks to the hardware. So the hardware is made more generic, and then the software itself allows them to accomplish more specific things, and that's where they can do bug fixes and that kind of stuff. So 30% chance of a question dealing with hardware versus software versus firmware. So pretty easy hardware versus software, right? Hardware is super, super fast, but fixed. Software is relatively slow, but editable. Firmware sits in between. It's the punchline. All right. Who makes CPUs? Not on the test. Okay, we talked about instruction sets. You should understand the difference between an open architecture like Intel and a reduced instruction set, just from a conceptual level of what is an instruction set's goal. So an instruction set's goal is to be able to solve a generalistic problem for computers, right? So when Intel sits down or IBM sat down or any of these companies, when they sit down to design a CPU, they have to decide what is the minimum, let's say, collection of magic tricks required to solve, quote, all problems that a computer can solve, right? What's that minimum number of magic tricks? So they have to capture that in a list of magic tricks. Reduced instruction set approach says we're really going to find that minimum. Okay, what is the fewest number of magic tricks that we can work with? Where an open architecture like Intel is going to say, we care less about the minimum number and more about the flexibility of having the ability to do some things that are common extra fast. So you might be able to do step 1 followed by step 2 followed by step 3 in terms of 3 instructions, and maybe that happens at speed 10. And then you could have a single instruction that effectively accomplishes the same thing as those 3, and maybe that happens at speed 6. So they're a lot quicker. Well, slower in terms of nanosecond, whatever. It's better. It is a better approach to it. So you might have an open architecture that actually has those 3 individual steps and then has another magic trick that has those meshed together. Because those 3 tricks individually might be parts of other tricks. Whereas that one mesh together says this is a common thing that occurs, so we're going to go ahead and give you a specific magic trick for that to make things faster. And really that concept right there, this concept of open architecture, is kind of what leads to some of the when a new CPU gets announced, when Intel's able to say up to 60% faster, right? Well, they always start it with the up to 60% faster because it's going to be in a very specific or just a few specific situations where they've likely, instead of changed or removed an old magic trick, they've likely added a new magic trick that optimizes something that was very commonly done in another architecture. And up to 60% faster means that only newer software that's specifically compiled to take advantage of this new magic trick is going to be able to be up to 60% faster for that particular thing. It kind of makes sense? Okay, so understand that relationship between the instruction set and speed. The concept of a reduced instruction set versus open architecture, I don't know if I'd ask something very specific. Well, I do like the concept with reduced instruction sets that having fewer magic tricks, kind of shooting for that minimum number of magic tricks, does then make the compiler design more complex. So writing a compiler for a RISC processor is a more difficult task because you're having to go through a lot more hoops to really create those granular instructions to solve the problem, since instructions tend to do more things per instruction. I think I asked that in a quiz at some point. I think I was on a quiz, so maybe I won't ask that on the test. But the idea of instruction sets in general, with that idea of capturing the magic tricks that will solve the general computing problem, that would be fair game. All right, yeah, so here's our thing here. Yeah, I mentioned this before, the whole parallelism thing. Also more of maybe an operating systems discussion when we talk about the performance of a chip. So probably not something I'd ask on an exam as it relates to what I want, the competencies I want you to come out of this class with. All right. Same thing here. This is all in that category of. Okay, so this stuff I would just say, obviously, all my exams in any class. I mean, if my class was basket weaving, it's going to have at least one conversion question on it. Okay, so there will likely be several conversion questions on this exam. So you should be able to move between sizes. So the bit-based things and the byte-based things. So if I ask you how many bits in 11 gigabytes or something like that, you should be able to do that conversion. So be able to work with that, the sizes of things, because those are things that are very important to us when we deal with memory sizes and data rates and things like that. When we're to start talking about data rates going from cache memory, we've already kind of talked about the idea of, the closer to the CPU memory is, the faster and smaller it tends to be. So registers are super fast, where L1 cache is a little bit slower, L2 cache is even a little bit slower, and so on and so forth. Now, we did talk about L1, L2, L3 cache, right? Okay, so if there was one aspect dealing with multiple cores that could make an appearance on the exam, it would be the concept of L3 cache. Does anybody know why? Go ahead.
It's shared between different cores.
Yeah. So L1 and L2 cache live on an individual core. So they're part of a core. L3 cache is part of a processor and is used and is shared between multiple cores. All right, so it is kind of a newer architecture type of approach. Not brand new, since multiple cores have been out for a while, but it's a way of quickly getting data between cores. The use of L3 cache would really be a operating systems type of concept. The existence of L3 cache being shared between two cores would be fair game on the exam. I don't see it as a high likelihood, but it would be fair game. All right? So, be able to convert this kind of stuff. Be prepared to pay close attention to the big B versus little b. Big B means bytes, so that's packs of 8, whereas little b means bits. All right, so pretty high probability that if I have you convert something with sizes, I'm going to ask you to switch columns. So you'll be going from bits to bytes or from bytes to bits, one of those things. So be prepared to look for that. Yeah.
Is it possible for you to ask us to say how many nibbles or something we're not worried about?
Well, possibly. I mean, you should know that a nibble is 4 bits. But I don't think I'd ask it on a conversion question like this. So you should know the concept of a nibble, know what that means. It might come up in a numeric conversion question, converting between hex and binary, because with that you use groups of nibbles, right? But for something like this, I probably wouldn't say, I don't even know how I'd ask that. Yeah, it'd be a really strange question, right? Yeah, not related to this. So yeah, you won't have to worry about that for this. But if you want to do the trick of hex to binary or binary to hex, you should be comfortable with nibbles. If you are glutton for punishment and don't want to do the trick, then you don't even need to know what a nibble is. just roll with it. All right, so certainly concept of memory. From a generic perspective, you should know what memory is, how we, kind of the concept of what makes memory good. So I think good means different things, right? Just like I think at some point, whether it was in this class or another class, we talk about what makes internet good. Is it maximum download speed? Is it latency? All these different things that might be good for different people. So maybe having a lot of capacity is good for somebody. Maybe having really fast speed is good for someone else. I think we probably talked about that example if you've ever seen, you've been buying a laptop, and this was kind of more common when we still had mechanical drives. Now everything's pretty much a solid state drive unless you've gone real budget pleaser on a laptop. But when you have mechanical drives still in the laptops, you might see a machine that came with a terabyte hard drive, or you could upgrade to a 512 gigabyte hard drive. And the difference is that terabyte was like 42 or 5400 RPMs. The 512 gig hard drive was 7200 RPMs. Spun faster, which gave you more speed, read-write speed on the hard drive. And very interesting thing is, I think we mentioned this in class, and this is more trivia knowledge, is that assuming you have enough memory for your computer to operate, probably the place where you will feel the slowness of a computer the most is with a slower hard drive. So if you have a mechanical hard drive in a machine, and so let's say you have a computer at home that you feel like, it has pretty good parts in it, have a good graphics card, have plenty of RAM, stuff like this, but it just feels slow. Go out and get an inexpensive solid state drive, and your machine will feel 100 times faster. That's where you feel it the most when you're using a computer. You're not going to notice the difference on a daily basis between 2.4 and 2.5 gigahertz on the processor, right? That's more of something that shows up in a benchmark or something like that, but you will feel hard drive performance. All right, so memory means many different things. So that can mean anywhere from our RAM to our registers to a hard drive, right? It's a place that holds things. Typically, the larger the capacity, the slower the speed. Faster the speed, the smaller the capacity. Closer to the CPU, the faster and smaller memory gets. Also, the more expensive it likely gets. That type of thing. Okay, so this slide here would be kind of maybe high-level knowledge of memory. Fair game. Certainly fair game. I could see asking a question in that ballpark of what I just talked about, where what are different ways of, why might somebody be more interested in capacity of a hard drive versus in the speed of a hard drive, right? So, capacity is, if you go out and buy a gaming computer today, a lot of times these machines have 2 hard drives, right? They have a smaller solid state drive. Maybe it's a 128 gig hard drive or something like that the OS lives on, you install your games and stuff like that on. And then it has a 1 terabyte mechanical drive for you just to throw all your data files on. That's where you keep your music and your images and all sorts of stuff that aren't impacted by speed. All right, so kind of understand those concepts. All right, so here's kind of our walking path of memory in terms of speed. So we have our registers super fast, L1 cache a little slower, L2, L3. Then we have our system RAM, and then we have our hard drive. We can keep going. We can go to like CD-ROMs. I mean, that's our DVD burners now. And then, do they even sell CD-ROMs anymore?
Yeah.
Do they? Who uses those?
I honestly don't know.
Yeah, interesting.
You can't fit anything on them.
Well, it used to be that was huge. Do you know what the capacity of a CD is?
These days, about 750 megs.
Yeah, so when it started, it was about 640 megabytes. Yeah, and then you could do compression. Then they had the dual-sided ones, and then the DVRs came out. I mean, who even uses disk drives anymore? It's almost like used for a cup holder, right? What's this? Yeah, I always wondered that too. Like, so I mean, I got a new car like 3 months ago or something like that, and it has I think it's a DVD. Do people actually put DVDs into cars?
Yeah, to watch some like.
Well, not in the front.
Passenger.
Okay, hold on. Now, okay, now it got me thinking. Because I have, it gets a little sketch when I'm, on a long trip when I'm streaming DirecTV or Netflix or something like that. Obviously I'm doing it while driving, but only on country roads or heavy Chicago traffic or all the time. Yeah, but in any case, it doesn't make sense to me why there's even physical discs anymore. I try to avoid it like the plague.
Backups to backups.
Backups to backups.
There have been many times where my only option is to use a physical CD to restore someone's system.
I see. If you're going to go really old school, you probably still can buy like USB-based floppy disks, floppy drives.
Yeah.
But you probably can't buy floppy disks anymore. Or if you can, they're probably really expensive because they're like collector's items.
Yeah, I haven't seen any. I have, however, seen a brand new pack of cassette tapes just sitting in my
Really?
Yeah.
Why would they sell cassette tapes at Meijer? I mean, I can see it like at Goodwill.
I don't know.
But if it's in Meijer, that means they are getting recent stock. You found floppies?
Yep.
$10 for how many?
10.
1.44 megabyte? Or are they the dual capacity? Right. All right. So,
You can find 5 1/4, let me know.
there were ones bigger than that. There were these giant. Oh, yeah. All right. So, understand that concept that the closer to the CPU you get, the faster and more expensive and smaller memory tends to get. Probably the two memories that we care the most about in here is going to be registers and RAM. That's our sweet spot. We've seen that more recently as we have been exploring the ARM instructions. All right, so chances are, if I asked you more specific questions about memory, it's going to be in terms of registers and RAM related to ARM. If I ask you a generic question about memory, it might be the concept of fast, closer to the CPU, the faster, and the smaller and the likely more expensive. I would say it's in the realm of possible that I would ask you to list the memories, list the 4 memories leading out from the CPU from the slowest to from the fastest to the slowest or something like that.
Is a good question.
I would say that would be an okay question. I would need a filler. It would need to be a filler question. The chances are in this class, if I need a filler, I'll just put another conversion question. I love conversion questions. And this is the class for conversion questions, right? Finally, it's a sweet spot. All right. I'm not going to ask you anything about pixels. When we talked about it in terms of size capacity. Well, I mean, really, we were talking about this in terms of, data rates, I think, stuff like that, which actually might come more into play in the second 8 weeks, just for one example, actually. But for the exam, nothing about pixels. You should certainly be familiar with an ARM. Okay, and we'll let Tim. Yeah, I knew when I said that it was going to be. Okay, you should be familiar with ARM architecture. Just the idea. Question: is ARM architecture an example of open architecture or RISC architecture? See, I'm asking that question. I'll tell you the answer after you try to answer it. We definitely talked about it.
We don't have any notes on it.
Well, then you didn't take notes of what I talked about. Go ahead.
It'd be risk, wouldn't it?
Well, now you're asking me a question. When we talked about this, we were talking about PowerPC versus Intel processors. So we kind of talked about, so PowerPC processors, what Macs used to use, they used a reduced instruction set and it kind of failed. And that's when Apple went to the route of Intel. You know, they were trying to save their company. Just made more sense. So for a long time, there was this mindset that reduced instruction set processors were kind of a bad idea. But now we've come full circle, and now all the processors that are in our mobile devices are ARM-based processors. Apple processors are ARM. The Snapdragons that are in most of your Android devices are ARM processors. Why do you think that is? Or why did I tell you it was? You remember this conversation, right?
No, you haven't given us the answer yet.
Well, I gave you the answer weeks ago. We talked about this in class, right?
I'm
We
remembering
just
some
talked
of
about
it
the
now.
difference between the two.
No, we talked about the
Oh, we
specific example.
absolutely talked about-
Definitely
I probably
remember
spent
talking
20
about
minutes in
Snapdragon.
class talking about this story. See,
Then it obviously
she doesn't pay attention to me.
makes
She's probably sitting there doing math homework or something.
math.
Yeah, usually.
Well, you should. If anybody's going to do math homework in class, you should be using as though you're saying you're missing assignments. I mean, at least be productive is what I'm saying. If you're not going to listen to me, be productive in class. Why do you think our mobile devices today have gone to ARM processors? Go ahead.
Because they're smaller and will produce less heat.
Yeah, fewer magic tricks, less electricity is kind of a, mostly a fact thing. Yeah.
Fun little story. One of the first kind of editions of a RISC architecture was able to power itself just off the data pulses alone.
Oh. So from the heat from the data pulses?
Yeah, the electricity of the data was enough to power the first RISC processor.
Interesting. Yeah, I'm trying to think how, because it would have had to have been based on a similar technology to like the telephone system that carries a voltage. Otherwise, it's a chicken or the egg problem.
Right.
You can't have data arriving if you don't have power to the thing to receive the data. But yeah, it is interesting. But yeah, I mean, the punchline is that now we care about devices that are running off a battery that fit in your pocket. So now all these things that used to not really be that important, battery life, power consumption, all these things now become a lot more important. So now maybe some of the negative side effects of ARM, harder, the compilers are more difficult. That just because they're more difficult doesn't mean we can't write them, right? So it's harder to write a compiler, but we got it right. We're mostly right, whatever. So these are very appropriate for mobile devices, and that's the direction we're moving. And we're even seeing it go into a hybrid mode now. I think we probably mentioned the Microsoft Surface Book. There's this guy in the middle now that is running an ARM processor, and you have to run a certain special version of Windows 10 on it that supports that. So we're seeing this overlap now where we're moving farther and farther from desktop and more towards our mobile stuff operating as desktops. We've seen that recently with Apple's iPad Pro and the Microsoft Surface Books are kind of the competitor to the iPad Pro. So we're seeing do you really need a laptop, or is a high-powered tablet actually what you really need? That type of thing. All right, so
So it's risk.
the answer is risk. Risk in our phones.
Yeah,
Risk is in the name.
Yes, the Acorn RISC machine is a RISC processor.
Yeah, so your phones have ARM processors in them, and ARM processors are RISC processors. Okay, yeah, so nothing about pixels, nothing about the memories. Well, yeah, something about memories, yeah. Am I pushing in the wrong direction? Did that, we did that. Nothing about pixels, ARM. Yeah, so now we start getting into registers and we start talking about bit spaces. These are definitely in play. Anything that looks like binary is in play. Is in play. So when I talk about an 8-bit register, that register can hold a total of 8 bits. How we utilize those bits, because now we have to start thinking about data representation, right? We've talked about some of these things in the last several weeks, last 3-4 weeks, where we might choose to use 7 of the 8 bits to represent negative numbers, for example, by encoding in 2's complement, stuff like that. So now we're giving up magnitude to give ourselves sign numbers. Make sense? So, but when we talk about an 8-bit register, so for example, if I say on the exam you have 2 8-bit registers, do something with these, you have 2 registers, each of them capable of holding 8 zeros and ones. All right? So, as an example, an 8-bit register can hold the smallest value of an unsigned number can hold is a 0. Largest value of an unsigned number is 255. So that would be all ones. If I'm doing 2's complement, we saw 2's complement, right? It's negative 128 to positive 127 is my range of values that will fit in there because I'm encoding my numbers using 2's complement, utilizing all 8 bits, but using one of those bits to manage sign. I don't think I'd asked a question about this. This is kind of where you were getting at, like nibble and stuff. It's not that this is unimportant. It's that nibble is always 4 bits. A byte is always 8 bits. But this idea of a word and a double word does change depending on architecture. In fact, I think when I first explained it, I explained it wrong, and you fixed my numbers, right? Yeah. So if I don't know it, I can't ask you to know it, right? So I won't ask you about words and double words. If I explicitly want something, I'll tell you the bit size, okay? But that does change with architectures. So when we talked about arrays, we were talking about, this was kind of our precursor to that idea of offsets from memory. So we reminded ourselves how arrays work in software. So I'm not going to ask you about arrays from a programming perspective, but by reviewing arrays from a programming perspective, we were able to then go and see those ARM instructions that give you a base address and then an offset from that base address, because arrays work that same way. All right, so this was our explanation of that, which then allowed us to look at the load and store instructions. And when we're storing something into memory or loading something from memory, we are where we're getting it in memory is represented by a base address and then an offset from that base address. That's what you should be comfortable with. Okay, if I show you some ARM instructions that does that, or if I give you kind of a representation of memory, and I say what value exists at I kind of give you the base address offset by 16 bits or something like that, you should be able to walk through memory and give me that value. Kind of prove you understand the concept of offsets off of base addresses. Make sense? Okay, so load and store instructions. Know those guys. Certainly be able to convert binary to everything, decimal to everything, everything to everything. Okay. There will at least be 2 questions on there that directly involve Klingon. Awesome. It actually would be fair if I gave you the character set. Won't be Klingon. Okay. Standard stuff. You will be limited to the English alphabet. So A through Z is the maximum you'll have to go. After that, you can start working with like Pac-Man symbols and hearts and stuff like that. But
Have to work in Hebrew.
I don't remember any of that. So I had to take Hebrew classes when I was a kid. So it's like, why do you forget those things? How many of you have had? You've had Hebrew, right? I mean, you just had it like last year, right? Or are you in it now?
Yeah.
You're in it now. You had Greek last year.
I had it last year as well.
Oh, okay. Why is it so easy to forget? The only thing I can do is a little Hanukkah saying. Most of you knew I was born Jewish, right? Yeah, so I grew up with learning all that stuff, and I had to go to Hebrew school and learn.
Wear a little hat on your head.
Yeah, I don't know any of the words anymore. I just know the saying you're supposed to say before you light the candle and get the present. Funny stuff and true. Yeah, so again, reviewing hardware registers, know that they're super fast, super expensive, super small, but that's where, if we're going to operate with real-time values, our magic tricks feed off of registers. That's what they do. And when we move something from memory, so earlier I mentioned that kind of our two go-to moves that are memory related are registers and system memory. When we want to work with something, we load it from system memory into a register so that we can work with it quickly. Okay, that's the go-to move. So if you kind of think about this in the broader computer science perspective, when you throw operating systems into this, what do? When we double click on an icon, stuff is loaded off of super slow memory, your hard drive, into faster memory, system RAM, and then when it gets eaten by the CPU, an instruction will grab it from system RAM and load it into a register to be consumed or something like that. That makes sense? So kind of our cadence is go from slower memory to faster memory with the understanding that we have limited space in faster memory. So we need to be good stewards of that and only move values in when we need them and that kind of stuff. We talked a little bit about embedded systems, but I don't think I'm going to ask anything about it. So this is kind of our, we were talking, I think where this came up is we were talking about the kind of limited memory sizes. Where in general, when we think about our computers today, we think about like, oh, we have 16 gigs of RAM, who cares? We got plenty. But when we think about some embedded systems today, like a little computer that runs your dishwasher or something like that, you have to solve problems much more similarly to like what we had to do in like the early days of computing when memory was really expensive. We didn't have a lot of it. Okay, because we might only be buying a chip that has 32K of memory on it, just because that's the cost-effective thing.
No one really needs more than 640K of RAM.
That wasn't his quote. I think his quote was 32K, right? Bill Gates?
640.
You sure?
Yep.
You might be right.
I just Googled the number because I
Oh,
also
did you?
thought it was lower.
I can blame it on being old. You can't do that, but I was also alive when he said it. All right, so I won't ask a question about embedded systems. It's more of a, I mean, it is important, but not a competency I necessarily want to test you on. Just understand that we do still have miniature computers in some of our smaller systems today that are domain specific, that we do have to think about problems in terms of how much will fit in memory on that particular thing. Same thing, Internet of Things. I think that is where it came up. We were talking about computers inside of your toasters and stuff like that. Interesting stuff, not on the test. Yeah, so when we talk about CPU architecture, if somebody's giving you that, kind of the laundry list of, what makes a CPU, it's going to be your instruction set. What registers do you have available to you? Because the instruction set works hand in hand with those registers, right? Because a lot of those instructions require you to give it registers as various inputs so you know where you're grabbing stuff from or storing things to. So in ARM, we have 31 hardware variables, 31 registers, and 1 0 constant. So we have a register that's always 0 that we can use. And then we have an onboard memory of 2 to the 62nd. I think I would probably question that before. It's giving up 2 of the bits for something else. I bet you they use it for like overflow or something. But we really haven't talked about uses for cache yet. We'll talk about that in the second 8 weeks. So nothing about cache on the exam outside of that L1, L2, L3 exist. Those are cache memories, but not necessarily what they're for. Again, for ARM, this was the given information, but I'm not gonna, if I want you to work with a 32-bit value, I won't use the word. I'll say 32 bits. All right, so I'll be specific about this, the bit space that you're dealing with. So this is where we were talking about memory offsets, base address to, doing walks. So this is a base address of x2. Take 4 steps forward. So base address is 100. 1, 2, 3, 4 puts us right here. That's where a 7 lives in this case. Okay, so that's that kind of maneuver of starting at a base address and then having an offset from that base address. And that's what's like arrays when we learned about arrays from a programming perspective, but it's also how our systems actually work. Know what an immediate value is. This is a literal, a number that you are going to put into something rather than the source being a register. And with ARM, we have in the instruction set, we have different instructions for whether or not we're adding 2 registers together, storing the result, or storing the result in a register, or adding a number plus an immediate together, storing the result in a register. Those are different magic tricks. So when I say immediate value, know what that is. More conversion stuff, be able to do all that stuff, all the different directions. You should be able to perform left and right shifts. I probably won't ask you, I definitely won't ask you about the use of them, because we're not really going to see that until the second 8 weeks, like an effective use of them. So if I say take a binary number and shift it left 3 times, you should be able to do that. I don't necessarily see myself doing that. Again, it would be a desperation question, and at that point I would probably throw another conversion on there. So we don't really have enough context for shifts yet, but I'll call it fair game. It's easy, but bitwise operations I think will find their way on there. So you should be able to perform bitwise ands and bitwise ors, and bitwise xors, XORs. So a 1 and a 1 is a 1. A 1 and a 0 is a 0. A 0 and a 1 is a 0. A 0 and a 0 is a 0. And or if either one of them or both of them is a 1, the whole thing's a 1. An XOR, if exactly one of them is a 1, it's a 1. Otherwise, it's a 0. Okay, so you'd be able to do bitwise operations. Okay. So this is, again, offset stuff. There was our quiz on risk stuff. Yeah, see, this is where things started getting out of order, because this was like day 2 of class, right? It's in slide 41. Definitely the concept of storing negative numbers are 3 different approaches and what's wrong with them. So, sign and magnitude versus 1's complement versus 2's complement. What's the weakness of sign and magnitude in 1's complement? Yeah, we have 2 ways of representing 0, which maybe we can say isn't the end of the world, but why not use that extra bit space to represent something other than 0? Give us an extra unique value, right? So 2's complement allows us to get the extra unique value. So you should be able to work with 2's complement. You should know about sign and magnitude and about 1's complement in terms of its weakness in that you have a double representation of 0. But I probably wouldn't have you do things, like I probably wouldn't say store the number -7 in sign and magnitude. That would be a pretty easy question, but I probably wouldn't tell you to do that. If I'm asking you to show me that you can do something, it would be in 2's complement, since that's how computers really work, and that's what we spent some time writing and things like that. Make sense? All right, so be able to do 2's complement stuff. Old slide. Why did I say that? I mean, I realize it's, no? What?
Even more confusing, your battery is low.
Yeah, I know. I think we'll make it. Ish. We'll be close to making it. What's it?
It's mostly battery, right?
Yeah. My Mac will sleep soon. So that's what happens when I didn't have the whole thing charged. So, be able to deal with sign and magnitude. Here's our nibbles as far as they go for converting, well, here's our sign and magnitude nibbles, I guess. But I won't ask you to write anything with sign and magnitude. It'll only be 2's complement. What? Oh, go ahead.
I just wanted to confirm that 2's complement, to code it, it's flip the bits, then +1. To decode, it's -1, then flip the bits.
2's complement is flip the bits, add 1. And then to decode it, it's flip the bits. No, it's subtract 1, then flip the bits. Or if you read closely in the book, there's a trick. Instead of anybody know what the trick was? So to encode it, you flip the bits and add 1. That's set. To decode it, you could subtract 1 and then flip the bits, or do what?
Do the convert from binary to decimal. Decimal.
Oh, the Maddie cheat. Yeah, I remember that one. Okay, what's the real trick? Go ahead.
You just flip the bits and add 1.
Flip the bits and add 1. So if you flip the bits and add 1, it's the same thing as subtracting 1. That's the trick. Remember how hard subtracting was? So you can flip the bits and add 1 to decode.
And
Huh? Encode is flip the bits and add 1. Decode is, flip the bits and add 1. All right, so be able to do these complement things. 2's complement I want you to work with. So again, with signed numbers, be able to work with that stuff. Yeah, so you should know what the range of values that'll fit. If I say, what's the range of values that'll fit in a 16-bit register if we're storing signed numbers, you should know that it's plus or minus 2 to the 15th power because we're using one of the bits for a sign. So that's, you don't have to memorize negative 32,768 to positive 32,767, but plus or minus 2 to the 15th power is sufficient, recognizing that one of the bits is going to be utilized for storing a sign. Not here, not here, sort of. Yeah, so, I was kind of connecting this back to our programming language stuff where we have a high-level, low-level machine language. And really, when we think about using registers, we're actually using bits as a data representation language, right? It just happens to be related to math, but we can use the same register for different purposes depending on what we're trying to accomplish. A register itself does not dictate what we put into it. Just like if you get a storage box from Home Depot, you can put different things into it and you're bound by the size of that storage box. Make sense? All right, so we have 2 different shortcuts for conversion that you might want to keep in mind. So we can go binary to hex using nibbles, and we can go from octal to binary or binary to octal using 3 bits. Okay, so 4 bits, a nibble is binary to hex and hex to binary. 3 bits is octal to binary, binary to octal. All right, so this is the stuff we talked about more recently. I probably will not get into this. I'll probably stop short of the ARM instructions since we're just kind of getting into that now. We don't have a lot of context to really ask questions about it. So I would say this would be on the final, so don't worry about that for right now. And this is getting into these are our filler slides, but then this is kind of we started writing the Android application last time. All right, so I'm going to go ahead and start saving this, but are there any questions about